Hello, my name is Boris Sowiegraj, and with my friend Piotr Menclewicz, I would like to welcome you to a presentation of how did we build a data analytics platform for a Asian telecom, while also creating new and deploying existing analytics on the platform. So where did the project start? The project originated pretty much from the fact that we, as Gating Data, already set up stream processing with Flink for this specific client. The project was successful enough and produced enough good results that the client decided to make a next step. What was the natural next step? The natural step was to start storing the data. So we decided to take part of the cluster, divide it into stream processing to support the existing process, and the data warehousing, where we could start processing the data in a more kind of a batch or on-demand way. And here we decided to go mainly with Hive for storage and processing with SQL, and Spark for more advanced analytics in the future. Beyond the data warehousing, the client posed us also with a few analytical problems. Some more simple, like for example, aggregation of the data from the stream processing into hourly and monthly data, and some slightly more complex, like for example, producing business reports, or finding solutions to problems like how should the client evaluate cost of incidents in his network, or how to evaluate cost of service that he is delivering to the clients. Beyond solving those problems, we also were trying to understand what was the infrastructure on which client was working, because the basic knowledge that we have was that there is a data warehouse in Oracle set up on a server farm, which is a local server farm. But it's, of course, wasn't a big data environment, but an environment that we will be in the future also using, in the sense of taking out data from it, as we didn't want to limit ourselves to the stream data. So having set up the infrastructure and building the necessary SQLs, we also proceeded with the project in terms of defining an algorithmic approach to the cost of service and machine learning approach to the cost of incident. Having had that, we also had some discussions with the client about what is his current analytical setup, what is the client's experience with big data, because while the team that was supporting the stream processing existed, there was also the new team that we were onboarding that hasn't had any touch of work with big data. And aside from that, we also were thinking about how to best expose the data that we are collecting in the cluster for any kind of business use cases that the client had. So how did we go about it? We firstly tried to map out the existing production models, the models that are being currently developed, and the pipeline as the client sees it at the moment. We dug into what kind of infrastructure is being used, and we found that it was pretty much infrastructure built on two parts: a standalone server machine to which local computers were connected and divided up, and people divided up the work between the external machine and local machines, something that wasn't really compatible with the big data environment and big data sets that we wanted to work on. So the first proposition was to set up a Workbench for analysts, and we decided to do the first setup in the simplest way we could find. So set it up as a virtual machine on which a Jupyter Hub was deployed, which was serving Jupyter Lab instances to analysts with customizable environments that were defined in the Docker images, but also the clients, analysts, and us had ability to flexibly define new things that were that could be run inside the Jupyter Hub. And it meant both libraries, but for example, also applications in Dash. We also knew that there will be a need to move data between Oracle and the new data lake. So we decided to deploy Scoop in order to facilitate this moving of data. And for better exposure of data to the client, we went with Power BI. We also started looking into what kind of models could we move to the cluster as the best use cases for both showing the capabilities of the cluster, but also for learning purposes.
Okay, so the first chance to test the platform in practice was trying to implement the first model and move it from the old infrastructure to the new one. We've chosen customer segmentation model based on k-means because it was relatively simple and frequently used. Originally, it was written in Python and hosted on a standalone server machine. For the first approach, we tried to spend as little time as possible rewriting the code. So this is why we've chosen to use Koalas. Koalas is a library that allows you to take a pandas code and run it as if it was a Spark application. It should be possible at minimum effort. However, in our case, with the version of the library available at the time, it still took a while to refactor all the code to make it work. And even after making it work, it was still performing worse than the original version. This is why we decided another approach, and we tried to rewrite the whole thing into a native Spark application. It took a while, but eventually we've managed to make it work and also reduce the computation time by 60%, which is about an hour. So at the very first glance, it seems like a successful use case because everything worked and the performance was even better than before. But actually, there were a couple of things that we didn't like in this process. First of all, rewriting the model took a lot of time and human effort. So this approach was really not scalable very well. On top of that, most of the data scientists in the team didn't know Spark, so they would need to learn a new tool in order to do the basic modeling in the platform. The last thing was related with switching the whole pipeline into a distributed manner, because it would limit access to the most comprehensive and most popular data science tools like sklearn, PyTorch, and so on. So after implementing this first use case, we took a step back to rethink the approach to the platform in general.
Okay, so having deployed all of the changes into the infrastructure and deploying the first model, we also facilitated some learning in terms of helping the client to understand how does the cluster work, how to do some of the processing with Hive on his own use cases. And in this case, cost of service was the thing that we were showing to the client, and how to do some basic operations in Spark. We did also some more digging into what kind of data sources were inside the client's infrastructure. And we found that there are multiple other databases that we should facilitate connections to or be able to move data from. And we decided to go have a multi-database with an engine that was able to query multiple databases at the same time in Presto. And also because we saw that connection to the Power BI to the cluster wasn't so easygoing, we decided also to deploy Superset as something that could both use Presto and develop and allow for developing new analytics, new visualization for analytics inside one tool for both querying and visualization. We also dug deeper into what kind of analytics has been done. We learned from our challenges with the RFM, and we decided that there is a need to do something more about what kind of environment is set up for work for the analysts. So digging deeper into the subject, we have posed a few demands on what kind of next iteration we would like to see as the environment for analysts. So those demands would be a flexible environment to deploy new tools, because while analytics for machine learning was set up well with Jupyter and Spark underneath, there was still a need to, for example, set up some Dashup, set up Presto, set up other applications. So we decided that to really build a useful analytics workspace for the client, we need flexibility in deploying new tools and testing them out with the client. We also wanted something that would allow us to dynamically scale the environment for the client, because we shouldn't be always depending on Spark. In order to move models quickly, we wanted to have ability to deploy models and adjust the amount of RAM that was provided, for example, to the client so that he could use his existing Python codes. Beyond that, the only scheduler that was currently existing at the client side was NiFi without any kind of API interface for creating pipelines in an easy manner, in a code manner. And we also wanted something like that. And we wanted not to build everything from scratch, but we wanted some kind of support for both operating and extending capabilities of the platform. So in order to provide that, we decided to go with setting up Kubernetes cluster next to the Yarn cluster, because they were able to work together well. There was no problem with setting up new tools or allocating resources to any kind of applications. And there is a lot of things already ready to manage such a cluster. And also to fit all of the analytical needs that we currently had, we decided to go with KubeFlow as a Kubernetes native platform that already integrates a lot of tools needed for modeling and machine learning, while also having needed interfaces for deploying customizable and scalable environments for modeling in Jupyter, and also delivering scheduler in pipelines that supported all of our needs. The growing community was also a plus. So having added this to the plan for our next quarter, we also had one more challenge to think about, meaning the client wanted us to think about how could we deliver a 360 perspective on the client. And so we worked on the infrastructure analytics and thought about the 360 client view. Having set up everything and having moved another model in the churn and deploying the cost of service productionally on the client's cluster, we have come back to the client with our idea about how could we address the 360 client view for the client. So what was our perspective? The perspective was that we will be storing the basic data, meaning the features, inside the data lake. We wanted some kind of a control interface to both schedule and retrieve the features from the data lake. And we aimed to build it in a way that building up new models could allow for adding to the knowledge already existing and reuse of this knowledge with building new models, allowing for a faster deployment of new models with already existing features and minimal work with adding new ones. Okay, so how did we structure the problem? So we thought about creating a setup in which the information has been integrated in reasonably one place, meaning that the currently disparate information in multiple data tables and potentially also multiple data sources in the sense of multiple databases, we wanted to bring everything into one place. We wanted also to have an ability to define the features and schedule their runs, so that if the feature has to be run every hour, every day, every month, we can have an interface for doing that. We also wanted an easy retrieval because, of course, we want it to be easier to develop new models, not harder. And because the infrastructure in the sense of data that is going to be brought into our solution will be growing, because we are expecting building more and more features that define the client, we wanted to be able to introduce people to these features easily and move around this infrastructure. All of this seemed quite natural fit the idea of feature store. And because there aren't many solutions for feature store, we decided to build our own. So as I said, the integration of data was supposed to be done in a feature store. But having already deployed KubeFlow, we decided that this is a very good setup for creating scheduling for the features inside the client's cluster. For retrieval of the features and some ideas about how to construct the flows, we used Feast, or at least its core, to better structure the heart of the platform. And for managing the metadata, so moving around the cluster, we used Amundsen. In the end, we also shown the client our perspective that while client and information about him is one thing, there will be also other knowledge verticals that we would like to serve with this setup. And all of this was compelling enough for the client that he allowed us to go forward with this vision. But having been closer and closer to the finalization of the contract with the client, we decided there are multiple things that would allow us to both make the work on the cluster easier and facilitate collaboration in a greater manner. So what we decided also to propose, we decided to propose developing a sync tool. So instead of using just Scoop, we decided to bring in a tool that we created on our own that allowed for defining imports for specific tables, scanning those tables to check if, for example, any changes were done from the last time that we were scanning the table, and retrieval in a scheduled manner. Beyond that, we decided to propose to the client that given that there are new practices in terms of developing code and new knowledge being created also on the code level, that a code library, a corporate code library would be beneficial for him. And we decided here to go with Nbdev that allowed to define the library in Jupyter, in the sense that all of the definitions of functions and the structure of the libraries were defined in Jupyter. And there was an easy transition into a web page that provided documentation of the library of code and also transportation to GitLab, from where the code could be both viewed and provided to the users for import as libraries. We also expanded our focus not only with trainings, but also with demos, and brought in some more training for the DevOps, so that they can not only analysts can use now the platform, but also the DevOps can support them. All of these actions came to life in the next 3 months. And also in the stream related to analytics, we added 2 new models for development and finalized development of the cost of incident.
Okay, so let's now see the first end-to-end machine learning project implementation in the platform, cost of incident. We will discuss all the stages of the project, from understanding business problem through modeling, moving to production, and interactions with the users. But first, let's understand the problem. So imagine a network of antennas, each of them responsible for handling your voice calls, messages, and internet traffic. What happens if one of them fails? Of course, you are not very happy, but what does it mean for your network provider? Since he is not able to provide the services, customers are not able to use them and pay for them. So it's quite intuitive that there's some kind of a loss. And the goal of the project was trying to estimate the value of this loss. Here we'll focus on the cases where lost traffic could be almost directly linked to the lost revenue. But it's very often not the case. There are many edge cases, like for example, handling with users that pay one fixed fee each month, regardless of the traffic. So now that we understand the problem, let's try to find the right data. Here we had 2 kinds of challenges. The first one was identifying the right data sources, because for example, traffic information was stored in a couple of places, and each place has slightly different information. So we needed to build some understanding of each data set in order to pick the one that was best for our need. The second challenge was technical one. We are provided with different data sets from different sources and in different formats. So we needed a way to handle all of them. Turn out that with Python and Spark, we are basically very flexible, working with any formats and any files, whether big or small. On top of that, we have used Jupyter environment, which provided extra interactivity, so we could really interact with the data and quickly build the understanding. Let's try to think about how we can frame our business problem as a machine learning problem. So let's try imagining 2 lines. The first one with the expected traffic, and the second one with the actual traffic. Most of the time, they should be very close to each other. But when incident happens, you should see a drop in the actual values of the traffic. So actually the gap between what we expected and what happened is our traffic loss. Since we know the actual values, the thing that we need to predict is the expected value of the traffic. Since this is a time series problem, we have used a Prophet model to try to make this prediction. Prophet is a library developed by Facebook that is designed to do specifically that, make time series predictions. And it turned out that for our use cases, it worked very well. The problem was that we didn't have one time series to model. We had literally thousands of them. And by default, Facebook Prophet does not provide inbuilt solution to handle that and to build multiple models at a time. So the way we approached this was using Pandas UDF, which is a Spark feature that allows you to take a Python function and run it on many machines in parallel. So to be a bit more precise, you just take a regular Python function, you define it as UDF using a decorator, and then you are able to apply this UDF on your Spark data frame. The way it works is splitting the whole big data sets into multiple chunks based on the grouping that you have chosen. And you run the Python function on top of each chunk. So in our case, we took we've built a dataset with all the incidents. We've used the Spark to divide into smaller chunks, one chunk for each incident. And then we use the Python function with the training pipeline to build a model for each incident. Okay, so now you should be able to run your calculations on many machines. The problem is that it's impossible to have all the libraries that you will ever need on these machines. So it was basically our case. We needed to have the exact Facebook Prophet library version installed on every machine that was unavailable. So how we approached this? First, we created a Conda environment that had all the dependencies needed. Secondly, we've zipped this environment and we have used Spark to send these environments to each machine before running the calculations. This way, we were sure that each calculation will work seamlessly. Okay, so let's now talk about moving this setup to production. While developing the solution, we ended up with many scripts and they were dependent on each other. So actually, the order of execution mattered. We had plenty of parameters that controlled the calculations that we stored in the YAML file, and everything was developed in Jupyter notebooks. So it was quite complex setup, and we didn't know how to move it to production. Thankfully, it turned out that we can use KubeFlow and its elements to do it very efficiently. Let's now talk about each of these challenges one at a time. So first, we couldn't use Jupyter notebooks directly because Jupyter notebook under the hood is just a JSON file. So we needed a way to extract the code from the notebook to more friendly form. So we've used nbconvert that took all this code and saved it as regular Python file that we were able to use in the production version. Then we've used KubeFlow pipelines to implement all the logic into a workflow that allows to make sure that if we trigger the calculations, all the scripts will run in a correct order. And finally, storing parameters in the YAML file is a good solution for technical people, but not necessarily for the end users. This is why we have used KubeFlow to build easy-to-use interface that managed all the parameters. It could also be used to trigger the calculation with push of a button. Finally, we've created interactive dashboard and we provided it to the users, so they were able to easily access the result, but also to understand the factors that contributed to the final results that they could see. So it had both geographical context as well as site context and incident context. Dashboard was developed in Dash and deployed on the Kubernetes platform. So these are all the steps that we've covered in our end-to-end machine learning project implementation using the new platform developed.
Okay, so going back from the detailed view to the big picture, to the already big stack of things developed for the client, we added the feature store with a few demo features deployed for the client and an onboarding procedure that we have prepared for specific for the client. We also added the collaborative tool that allowed from the sync tool to ease the transition between the old environment, which already was making difficulties for the client, to the new environment with much bigger processing power and capacities. We supplied him also with this library for corporate use that the new code patches were added and the library was being expanded. We added 2 more machine learning algorithms to the other 2 and algorithm for the cost of service. The not finished algorithm that was delivered was the next best offer. We started development and discussed where is it going next and handed over the development to the client. So after a year's work, we have pretty much set up a hybrid cluster that was communicating well between the 2 main pieces, Hadoop and Kubernetes. A lot of stack supporting the structuring, analytics, and modeling of data, while also thinking about the usefulness of the data in a manner that would be easy to use for analysts. We also were able to deploy quite a few solutions that would hopefully make the business for our client more valuable and easier to expand. So having said that, I would also like to say that we are expanding as an advanced analytics team. If you are interested in building analytical solutions on such infrastructures and cooperating with building such infrastructures, we are perfectly happy to talk to you, and hopefully you will be willing to join us and tackle the problems with us. For more information, you can see our careers webpage. Thank you very much.